All right, let's get into it. We're going to talk about one of the single biggest, most important upgrades in the entire history of the internet. The thing is, it's happening right now, mostly behind the scenes, without you even noticing. This is the story of how the internet is changing its fundamental address book to keep up with our hyper-connected world. It's a weird thought, isn't it? The digital world, it just feels endless. You can spin up a new website, create a new account, connect a new phone, a new smart TV, and it just works. But the system that makes all of that possible, the one that gives every single thing online its own unique home address, was actually built with a hard limit. A limit that, believe it or not, we've pretty much already hit. And there's the number, 4.3 billion. That's it. That was the grand total of unique addresses available under the original system, which we call IPv4. Now, to put that in perspective, there are over 8 billion people on Earth today, so we don't even have enough for every person to have one address, let alone one for your phone, your laptop, your watch. Back in the 70s, 4.3 billion must have seemed like an impossibly huge number. I mean, who could have guessed where we'd end up? Well, as it turns out, we did. Every single computer, every phone, every smartwatch, every server humming away in a data center, every single smart fridge, they all need an address. IPv4 was the bedrock. It's what the modern internet was built on. But its creators just never imagined a world where billions of us would carry the entire internet around in our pockets. The system was tapped out. So what do you do when you literally run out of numbers? You invent a whole new system, a much, much bigger one. So enter Internet Protocol version 6, or as you'll see it, IPv6. And this wasn't just some minor update. This was a complete, ground-up redesign meant to solve the address problem for, well, basically forever. You know, I love this quote because it has to be one of the biggest understatements in tech history. Saying its main strength is the large size is kind of like saying the main strength of the sun is that it's a little bit bright. The scale of this upgrade is almost impossible to wrap your head around. That is the number of available addresses in IPv6. It's 340 undecillion. Honestly, it's a number so ridiculously large that it doesn't even mean anything on its own. It's just massive. So how on earth do we make sense of a number like that? And this is the analogy that really puts it into perspective. We're not just talking about giving an address to every person or every device. We're talking about having enough addresses to assign a unique one to literally every single grain of sand on the entire planet and still have trillions upon trillions left over. So here's the key takeaway. We will not run out of IPv6 addresses, like ever. But here's the thing, IPv6 isn't just about having more addresses. It's about building a smarter, more efficient internet. For instance, the headers on IPv6 packets have a fixed length, which makes them way faster for routers to process. And instead of the old way of broadcasting, shouting a message to every single device on a network, it uses a more targeted multicast. It also replaces an old, clunky system for finding other devices with a much slicker one. It's like upgrading from asking everyone on the street for directions to just having a smart GPS that knows the best route. It is a genuine evolution. Now, this enormous address space unlocks one of the coolest features of IPv6, automated addressing. So how does your new phone or your laptop actually get one of these newfangled addresses? Well, in a lot of cases, it just gives one to itself. This feature is called Stateless autoconfiguration, or SLAC for short, and it is a real game changer. See, instead of your device having to go ask a central server on the network, hey, can I please have an address? It can just create its own valid address automatically. It just plugs in, listens for a second, and boom, it's one line. And here's how it works in 3 really simple steps. First, your device just listens for something called a router advertisement, which is basically the network's welcome message. Second, that message gives the device the first half of its address, the part that says you're on this specific network. And third, the device just makes up the second half all by itself, often using its own unique hardware address. And just like that, it has a globally unique IP address. No fuss. But there is a catch here. Because a device often uses its permanent, built-in hardware address to create its IPv6 address, that address never changes. And this means that device could potentially be tracked as it connects to different Wi-Fi networks, from the coffee shop to the airport to a friend's house. It's that classic trade-off, really. Convenience versus privacy. Okay, so this brings us to the biggest challenge of this entire upgrade. You can't just flip a switch and turn off the old IPv4 internet. It's It's everywhere. So for years now, and for many years to come, these two systems have to exist side by side. So how in the world do you manage a transition on that kind of scale? And that's really the multi-trillion-dollar question, isn't it? If IPv6 is so obviously the future, why aren't we all using it already? Well, the transition is incredibly slow, it's expensive, and it's just mind-bogglingly complex. It means every router, every switch, every server, every operating system has to be upgraded. So in the meantime, engineers have come up with some really clever ways to bridge the gap. The first and probably most common strategy is called dual stack. The easiest way to think about this is that it makes your device bilingual. It gets both an old IPv4 address and a new IPv6 address. This way, it can talk to either network without a problem. If it needs to reach an old website, it just uses its IPv4 address. If it's talking to a modern server, it uses the new one. Simple. Next up, we've got something called tunneling. This is what you do when a new IPv6 packet has to cross a part of the internet that only speaks the old IPv4 language. You essentially wrap the IPv6 packet inside of an IPv4 packet. It's kind of like putting a letter into a special envelope so it can travel through a foreign postal system. Once it gets to the other side, you just unwrap it and it keeps going. And finally, there's NOT64, which is basically a real-time translator. This is a crucial service that sits at the edge of a network and just translates IPv6 packets into IPv4 packets and then back again. This is what allows a modern IPv6-only device to still talk to a legacy server that only understands the old protocol. So, after all this complexity, these new numbers, these new protocols, this really tricky transition, what's the big payoff? What does this new foundation for the internet actually give us in the end? Well, one of the biggest benefits is just better organization. With so many addresses to play with, IPv6 allows for something called aggregation. This lets network operators group massive ranges of addresses together into one single entry. And what that does is it makes the internet's master address book much smaller and cleaner. And a smaller address book means routers can find paths more quickly, which makes the whole internet faster and more responsive for all of us. So here's a simple way to think about it. Instead of a global delivery service needing a separate entry for every single street in a city, it can just have one single entry for the entire city. It's all about grouping things logically. Now just imagine applying that same principle to the entire global internet. That's the kind of massive efficiency gain that IPv6 makes possible. At the end of the day, this is so much more than just a fix for a numbering problem. This is about laying a new foundation for the future. It allows for more efficient routing around the globe. It gives better support for our mobile devices as they hop between networks. And maybe most importantly, it's the only way to support the incredible explosion of the Internet of Things. A world with billions of smart sensors, cars, and home appliances simply cannot exist without IPv6. This transition from IPv4 to IPv6 is a slow, quiet revolution that's happening right under our feet. But it's fundamentally reshaping the bedrock of our digital lives, and it's opening up possibilities that we're only just beginning to imagine. It's a powerful reminder that even the most stable things we rely on have to evolve, and this evolution is setting the stage for the next great chapter of the internet.